Hello, class. I just wanted to clarify a common mistake I saw on the last quiz and the last practice, and that's concerning if friction's the only force acting on a system, as in you get something starting motion and then you stop putting that applied force and then it slows to a stop. Say, for example, you get your car going, stop pushing the gas, and then friction on the road slowly brings you to a stop. Does the mass of your vehicle or does the mass of your object matter for how far it goes? I think a lot of people are saying more mass makes more friction. And that's why you all were saying on the homework and the quiz that things won't go as far if they're more massive, if they start at the same speed. But I wanted to go ahead and show a demo to show you that the distance traveled is approximately the same if friction's the only force acting and you increase mass. So I've got this demo from PhET, which is a system from Colorado University. And so we're going to simulate with friction. We're going to get this up to speed by applying a force and get this box to the second big tick mark on the speed gauge. I'm going to change the box's mass after I see how far it goes, put more mass on top of the box, get it to the same speed, and see how far it goes. So to start off, there's a couple things I want you all to notice. Again, when it's not moving, remember that's the range of static friction. And static friction is going to be able to apply a force up to some maximum value. Notice how static friction always just opposes the force parallel to the box. It's not until I push hard enough, and then once I push hard enough, it starts to accelerate and the friction decreases for kinetic. I let go at the second tick mark. I'm going to see from the left foot of the person to the left side of the box how many of these cells to the side the box moved. So from the left side of the person, it traveled 1, 2, 3.5 the scale underneath the box. So I have some distance, 3.5 units that it traveled in distance after I let go when it was traveling at the second tick mark in speed, probably 2 meters per second. I'm going to clear the drawing and reset this back up, put mass on the box. So here's the initial condition again. I'm going to bring the speed gauge up. This time I'm going to make the mass of the box, mass of the system more. The coefficient of friction or the grippiness of the surface doesn't change because it's still a wooden box touching the grass on the ground. So notice that now, since it has more mass, compared to last time, note that the static friction can reach a higher maximum value. So when you use the static friction equation, which is normal force times the coefficient of static friction, you get a larger value. If it's not moving, does not necessarily mean static friction is more. Note it can be any value between 0 up to that maximum value. Then once it starts moving, it converts to kinetic friction. I'm going to get this up to speed. And then once it gets to the second gauge mark, I let go. Now let's see how far it goes. Went from the left side, 1, 2, 3.5. So notice how my left foot, I start at the halfway mark. Here's 1, 2, 3, and then this little mark's a half. It went the same distance. So here's the concept as to why it's going the same distance. Yes, friction doubles because the force into the ground doubles, because the mass doubled. So that means normal force doubled. So thinking force of friction is normal force times the coefficient of kinetic friction. A force of friction did double because the mass of the system doubled. So the force into the ground doubled. And so since the force into the ground doubled from gravity, remember normal force resists pushes into surfaces. So since normal force doubles, force of friction doubles. So since force of friction doubles, remembering the concept F equals ma, The first system, I'm just going to say maybe there was one force of friction resisting the motion, maybe 1 kilogram of mass. Obviously, the system is more than one, but let's just make every value 1. Friction was 1, mass was 1. Let's say it had an acceleration of 1. Now that it has double the mass, it's going to have 2 times the force of friction, but it also has double the mass. So look at what the system does. I have a 2 on the left, 2 on the right, divide by 2 both sides. It's still the same acceleration. It still comes out to the same ratio that it did before, the original F over the original M. The numbers just double for the 2 times mass case. It's still F equals ma. There's no change in acceleration based on how massive the system was. Going back to how things fall, remember that if you ignore air resistance, the rate something falls does not depend on the mass. So let's say you have a billiard ball from pool and you drop it at the same time you drop a bowling ball. Those will fall from that height and hit the ground at approximately the same time. No statistical difference. You can take a pencil and take a pen, drop them from over your head, let go, and they'll hit the ground at the same time. When things are being accelerated, just because of their mass, if they're, say, accelerating themselves due to some frictional force or some gravitational force, mass doesn't matter. The acceleration due to friction is constant, regardless of mass, just as if the acceleration due to gravity, as things are falling, does not depend on mass. So I hope that helped clarify the homework problem and the quiz problem, and I hope you all get it right on the test next week. Have a good day.